Hello there. Tonight, we are going to explore the most relaxing facts about stars to help you fall into a deep, restorative sleep. Above you, even now, even through the ceiling and the daylight and the atmosphere, stars are being born in clouds so vast that our entire solar system would be lost within them like a grain of sand in an ocean. These stellar nurseries have been creating suns for billions of years, and they will continue for billions more, patient and unhurried, following the ancient rhythms of gravity and gas. Tonight, you need do nothing but listen and let the slow birth of starlight carry you into darkness. Star formation begins in the cold, molecular clouds, vast regions of space filled with hydrogen and helium, and trace amounts of heavier elements drift through the galaxy at temperatures barely above absolute zero. These clouds are enormous. Some span hundreds of light years, containing enough mass to create millions of stars. Within them, the density is incredibly low by terrestrial standards, a better vacuum than anything we can create in laboratories on Earth. Yet over millions of years, gravity works its patient magic. Regions that are slightly denser than their surroundings attract more matter, growing slowly, imperceptibly, until they reach a critical threshold. Then collapse begins, and what was diffuse becomes concentrated. What was cold begins to warm, and the long journey toward ignition commences. The Orion Nebula, visible to the naked eye as a fuzzy patch in the hunter's sword, is the nearest large stellar nursery to Earth, only 1,350 light-years distant. When you look at that faint smudge of light, you're seeing a cloud of gas and dust illuminated by newborn stars, their ultraviolet radiation causing the hydrogen to glow in shades of red and pink. The nebula spans about 24 light-years, and within it, hundreds of stars are forming right now, this very moment, though the process unfolds so slowly that no human lifetime could witness significant change. The trapezium, a cluster of young hot stars at the nebula's heart, are only a few million years old. Infants by stellar standards. Yet they blaze with such intensity that they illuminate the entire cloud, revealing the intricate structures carved by stellar winds and radiation pressure. These stars will shine for millions of years more, but the nebula itself is temporary, a brief phase in the galaxy's ongoing cycle of creation and destruction. Within the densest regions of molecular clouds, gravity pulls matter inward, creating cores that will become protostars. The collapse is not uniform. The cloud fragments into many smaller clumps, each potentially forming a star or a small cluster of stars. As matter falls inward, it heats up, converting gravitational potential energy into thermal energy. The center of the collapsing core grows hotter and denser, while the outer layers continue to rain down, adding mass. This process takes time. For a star like our Sun, the collapse from cloud to protostar takes about 100,000 years, a mere eye blink in cosmic terms, but an eternity by human measures. During this time, the protostar is hidden within a cocoon of dust, invisible at optical wavelengths, but glowing brightly in infrared, detectable only by telescopes designed to see heat rather than light. The Eagle Nebula, some 7,000 light-years away, contains the famous pillars of creation, towering columns of gas and dust several light-years tall. These pillars are being sculpted by the intense radiation from nearby young stars, which slowly erodes the outer layers of the cloud, boiling away the gas and revealing the denser structures within. At the tips of these pillars, small dark globules mark the locations of forming stars, dense knots of matter that resist the erosive radiation, protecting the protostars growing inside. The pillars are beautiful, but they're also doomed. The same radiation that illuminates them is destroying them, and in a few million years, they will be completely dispersed, leaving only the stars they helped create. This is the nature of stellar nurseries. They are temporary, existing only long enough to birth new generations of stars, before being blown away by those very stars. Protostars are surrounded by accretion disks, flattened structures of gas and dust orbiting the growing star. Matter from the disk spirals inward, adding to the protostar's mass, while the disk itself becomes the birthplace of planets. The disk is not smooth. Instabilities and turbulence create spiral patterns, gaps, and rings, regions where dust grains collide and stick together, beginning the long process of planet formation. Jets of material shoot out along the rotation axis, perpendicular to the disk, carrying away excess angular momentum and allowing matter to continue falling onto the star. These jets can extend for light years, creating glowing shock waves where they collide with the surrounding gas. They're one of the most beautiful and mysterious aspects of star formation, visible in infrared and radio observations, revealing the violent processes hidden within the dusty cocoons. The temperature at the core of a collapsing protostar rises steadily as more matter falls inward. When the core reaches about 10 million degrees Kelvin, a threshold is crossed. At this temperature, hydrogen nuclei move fast enough to overcome their mutual electrical repulsion and fuse together, creating helium and releasing energy in the process. This is nuclear fusion, the process that powers all stars, the transformation of mass into energy, according to Einstein's famous equation. When fusion ignites, the protostar becomes a true star, generating its own energy, no longer dependent on gravitational collapse for heat. The outward pressure from fusion balances the inward pull of gravity, and the star reaches equilibrium, settling onto the main sequence where it will spend most of its life, burning hydrogen steadily, shining with a light that may travel across the galaxy before reaching anyone's eyes. The Carina Nebula, located about 7,500 light-years away, is one of the largest and most active star-forming regions in our galaxy. It spans over 300 light-years and contains some of the most massive stars known, including Eta Carinae, a stellar system so massive and unstable that it could explode as a supernova at any moment. The nebula is a chaotic landscape of glowing gas, dark dust lanes, and brilliant star clusters, a place where creation is happening on a grand scale. Massive stars form quickly in just a few 100,000 years, and they burn hot and bright, living fast and dying young. Their intense radiation and powerful stellar winds shape the nebula, creating cavities and pillars, triggering new waves of star formation in the compressed gas at the edges of the expanding bubbles. The Carina Nebula is a reminder that star formation is not a gentle process. It's violent, energetic, transformative, reshaping the interstellar medium and enriching it with heavy elements created in stellar cores. Not all stars form in isolation. Many, perhaps most, form in clusters, groups of stars born from the same molecular cloud at roughly the same time. These clusters can contain hundreds or thousands of stars, all gravitationally bound to each other, at least initially. Open clusters like the Pleiades are young, containing hot blue stars that haven't yet dispersed into the galaxy. Globular clusters are ancient, containing hundreds of thousands of old red stars that have been orbiting the galaxy for over 10 billion years. The stars in a cluster share a common origin, a common age, a common chemical composition, making them invaluable for studying stellar evolution. Over time, most open clusters disperse, their stars drifting apart as gravitational interactions and encounters with molecular clouds gradually unbind them. But for a few million or a few 100 million years, they remain together, siblings in the cosmic family. The interstellar medium, the gas and dust between the stars, is not uniform. It exists in different phases: cold molecular clouds where stars form, warm neutral hydrogen, hot ionized gas heated by supernovae and stellar winds. These phases are constantly interacting, transforming into each other, driven by the energy released by stars. Supernovae compress the surrounding gas, triggering new episodes of star formation. Stellar winds from massive stars sweep up the interstellar medium, creating bubbles and shells. The cycle continues, generation after generation, with each new generation of stars enriching the interstellar medium, with heavier elements created in stellar cores and supernova explosions. The universe began with only hydrogen and helium, but stars have transformed it, creating carbon, oxygen, nitrogen, iron, all the elements necessary for planets and life. Stars are not all the same color. Some glow blue-white, fierce and hot. Others shine yellow like our sun, steady and warm. Still others burn red, cool giants nearing the end of their lives, or red dwarfs that will outlive every other star in the galaxy. These colors are not arbitrary. They tell us about temperature, about composition, about age and fate. Tonight, we explore the spectrum of starlight, the rainbow of stellar colors that fills the night sky, and discover that in this diversity lies a kind of cosmic peace, a reminder that the universe creates in infinite variety, that no two stars are exactly alike, yet all follow the same fundamental laws. The color of a star is determined primarily by its surface temperature. This relationship is described by Wien's law, which states that hotter objects emit light at shorter wavelengths, while cooler objects emit at longer wavelengths. The hottest stars with surface temperatures above 30,000 degrees Celsius appear blue or blue-white, emitting most of their light in the ultraviolet and blue portions of the spectrum. Stars like our Sun, with surface temperatures around 5,500 degrees Celsius, appear yellow-white, emitting across the visible spectrum, with a peak in the yellow-green range. Cooler stars, with temperatures below 3,500 degrees Celsius, appear orange or red, emitting most of their light in the red and infrared. This spectrum of colors, from blue to white to yellow to orange to red, is a temperature scale, a visual representation of how hot each star's surface is burning. Astronomers classify stars using a system based on their spectra, the specific wavelengths of light they emit and absorb. The classification scheme uses letters O, B, A, F, G, K, M, arranged from hottest to coolest. The mnemonic, "Oh, be a fine girl / guy, kiss me," helps students remember the sequence, though the system has historical roots that predate our understanding of stellar temperature. O-type stars are the hottest, with surface temperatures above 30,000 degrees Celsius, appearing blue and emitting intense ultraviolet radiation. B-type stars are also hot and blue, though slightly cooler. A-type stars appear white, F-type stars appear yellow-white, G-type stars like our Sun appear yellow, K-type stars appear orange, and M-type stars appear red. Each spectral type is further subdivided into 10 numerical subclasses, from 0 to 9, with 0 being the hottest within that class. The Sun is classified as G2, meaning it's a G-type star on the hotter end of the G range. The spectrum of a star reveals more than just temperature. It also shows composition through the absorption lines created when light from the star's interior passes through its outer atmosphere. Different elements absorb light at specific wavelengths, creating dark lines in the spectrum that act like fingerprints, identifying which elements are present. Hydrogen creates a series of absorption lines called the Balmer series, visible in the spectra of many stars. Helium creates different lines, as do calcium, iron, sodium, and other elements. By analyzing these absorption lines, astronomers can determine not just what elements are present, but in what quantities, allowing them to measure the chemical composition of stars across the galaxy. Most stars are about 73% hydrogen and 25% helium by mass, with heavier elements making up only about 2%, though this varies depending on the star's age and where it formed. Blue stars are rare and short-lived. Their high temperatures mean they're burning through their hydrogen fuel at prodigious rates, fusing it into helium far faster than cooler stars. A massive O-type star might contain 50 times the mass of the Sun, but it will live for only a few million years before exhausting its fuel and exploding as a supernova. These stars are cosmic sprinters, burning bright and dying young, their intense radiation and powerful stellar winds shaping the interstellar medium around them, triggering new waves of star formation, enriching the galaxy with heavy elements. When you see a blue star in the night sky, Rigel in Orion, Spica in Virgo, the stars of the Pleiades, you're seeing a star that didn't exist when dinosaurs walked the Earth, and that won't exist in the distant future. A brief but brilliant flash in the cosmic timeline. Red dwarf stars, by contrast, are the universe's marathon runners. These M-type stars are the most common type of star in the galaxy, making up about 70% of all stars. Yet they're so dim that not a single one is visible to the naked eye from Earth. Red dwarfs have masses between about 8% and 50% of the Sun's mass, and their low masses mean they burn their fuel incredibly slowly. A red dwarf can shine for trillions of years, far longer than the current age of the universe. The smallest red dwarfs, just barely massive enough to sustain fusion, will outlive every other type of star, will still be shining long after the Sun has died, long after all the massive stars have exploded, long after the universe has grown dark and cold. They're patient, these red dwarfs, content to burn dimly for eons, the last lights that will remain when everything else has faded. The Sun's yellow color is actually somewhat of an illusion. If you could see the Sun from space, without the filtering effect of Earth's atmosphere, it would appear nearly white, emitting light across the entire visible spectrum fairly evenly. The yellow tint we perceive is partly due to atmospheric scattering, which removes some of the blue light, and partly due to the way our eyes and brains process color. The Sun's spectrum peaks in the green portion of the spectrum, but because it emits strongly across all visible wavelengths, our eyes perceive it as white or slightly yellow. This is true for most stars. Their colors are more subtle than the dramatic blues and reds we see in photographs, which are often enhanced to show the differences more clearly. But the colors are real, representing genuine differences in temperature and composition, even if they're more muted to the naked eye. Orange and red giant stars are evolved stars that have exhausted the hydrogen in their cores and expanded to enormous sizes. Betelgeuse, the red supergiant in Orion's shoulder, has a surface temperature of only about 3,500 degrees Celsius, much cooler than the Sun. Yet it's so large that if placed at the center of our solar system, it would extend past the orbit of Mars. Its reddish color reflects its cool surface temperature, but its enormous size means it's actually far more luminous than the Sun, radiating thousands of times more energy. Red giants are in the late stages of stellar evolution, fusing helium into carbon and oxygen in their cores, or in the case of massive stars, fusing even heavier elements. They're unstable, pulsating, losing mass through powerful stellar winds, shedding their outer layers into space. They're beautiful in their decline, these red giants, glowing softly in the night sky, reminders that even stars age and die. White dwarf stars are the remnants of stars like the Sun, the exposed cores left behind after the outer layers have been shed. They're incredibly dense. A teaspoon of white dwarf material would weigh several tons on Earth, and they're hot when first formed, with surface temperatures that can exceed 100,000 degrees Celsius, making them appear blue-white. But white dwarfs have no internal energy source. They're no longer fusing elements, so they simply radiate away their stored heat, slowly cooling over billions of years. As they cool, they change color, from blue-white to yellow to red, eventually becoming black dwarfs, though the universe is not yet old enough for any black dwarfs to exist. White dwarfs are stellar corpses, but they're not truly dead. They're still hot, still glowing, still contributing their light to the galaxy, just much more faintly than they once did. The Hertz-Sprung-Russell diagram is one of the most important tools in astronomy, a graph that plots stars according to their luminosity and temperature. When you plot thousands of stars on this diagram, a pattern emerges. Most stars fall along a diagonal band called the main sequence, running from hot, luminous blue stars in the upper left to cool, dim red dwarfs in the lower right. The Sun sits about halfway along this sequence. Above the main sequence are the giants and supergiants, stars that are more luminous than main sequence stars of the same temperature because they're much larger. Below the main sequence are the white dwarfs, hot but dim because they're so small. The Hertz-Sprung-Russell diagram is a map of stellar evolution, showing where stars spend most of their lives and how they change as they age. It's a reminder that stellar colors are not random, but follow patterns, that the universe is organized, that there are rules governing the lives of stars. The Sun is so familiar that we forget to marvel at it. It rises, it sets, it warms the air and lights the sky, and we take it for granted, this massive sphere of plasma that makes all life on Earth possible. But the Sun is a star, just like the distant points of light you see at night, and it's performing an extraordinary feat, fusing hydrogen into helium at its core, converting mass into energy, radiating light and heat across 93 million miles of empty space to reach us. Tonight we turn our attention to our nearest star, to the gentle rhythms that have sustained life on Earth for billions of years, to the processes happening deep within that golden sphere, processes so powerful and yet so stable that they've barely changed in 4.5 billion years. The Sun is a G-type main sequence star, what astronomers call a yellow dwarf, though it's neither particularly yellow nor particularly small. It's actually brighter than about 85% of all stars in the galaxy, most of which are dim red dwarfs. The Sun contains about 99.86% of all the mass in the solar system. Jupiter, Saturn, Earth, and everything else combined make up only 0.14%. It's enormous by terrestrial standards, with a diameter of about 864,000 miles, roughly 109 times the diameter of Earth. You could fit about 1.3 million Earths inside the Sun's volume, yet by stellar standards, it's thoroughly average, a middle-aged star of medium mass, unremarkable except for the fact that it's our star, the one that made our existence possible. At the Sun's core, where temperatures reach about 15 million degrees Celsius and pressures are 250 billion times Earth's atmospheric pressure, hydrogen nuclei are fusing into helium through a process called the proton-proton chain. 4 hydrogen nuclei combine to create 1 helium nucleus, and in the process, a tiny amount of mass is converted into energy according to Einstein's equation E to mc squared 2. The amount of mass converted is small, about 0.7% of the original mass, but because the speed of light squared is such an enormous number, even this tiny mass conversion releases tremendous energy. Every second, the Sun converts about 600 million tons of hydrogen into helium, and in the process, about 4 million tons of matter is converted into pure energy. This energy radiates outward from the core, taking hundreds of thousands of years to reach the surface, bouncing around inside the Sun, absorbed and re-emitted countless times before finally escaping into space as light. The Sun's energy doesn't travel directly from core to surface. The core is surrounded by the radiative zone, a region where energy moves outward primarily through radiation. Photons are absorbed by atoms, which then re-emit photons in random directions. This random walk means that a photon created in the core might take 100,000 to 200,000 years to work its way to the outer edge of the radiative zone, even though it's traveling at the speed of light. The path is so convoluted, so full of absorptions and re-emissions, that the effective speed is incredibly slow. Beyond the radiative zone lies the convective zone, where energy is transported by convection. Hot plasma rises to the surface, cools, and sinks back down, creating enormous circulation cells. These convection cells are visible on the Sun's surface as granulation, a constantly shifting pattern that makes the Sun's surface look like a pot of boiling water, though each granule is about the size of Texas. The Sun's surface, the photosphere, is what we see when we look at the Sun, though you should never look directly at it without proper protection. The photosphere has a temperature of about 5,500 degrees Celsius, much cooler than the core, but still hot enough to vaporize any known material instantly. The photosphere is where the Sun becomes transparent, where photons can finally escape into space after their long journey from the core. The light that reaches Earth left the Sun's surface about 8 minutes ago, traveling at 186,000 miles per second across the void. When you feel the Sun's warmth on your skin, you're feeling energy that was created in the core hundreds of thousands of years ago, that has traveled through the Sun's interior and across space to reach you. That warmth is ancient, patient, the product of processes operating on timescales that dwarf human history. Above the photosphere lies the chromosphere, a thin layer of the Sun's atmosphere visible during solar eclipses as a reddish glow around the Moon's silhouette. The chromosphere is hotter than the photosphere, reaching temperatures of about 20,000 degrees Celsius, a fact that seems to violate thermodynamics. How can the outer layers be hotter than the layers below? The answer lies in magnetic fields and wave energy, though the exact mechanisms are still being studied. Beyond the chromosphere lies the corona, the Sun's outer atmosphere, visible during total solar eclipses as a pearly white halo extending millions of miles into space. The corona is astonishingly hot, reaching temperatures of 1 to 3 million degrees Celsius, hundreds of times hotter than the surface below. This is one of the great mysteries of solar physics, the coronal heating problem, and while several mechanisms have been proposed, involving magnetic reconnection and wave heating, the complete explanation remains elusive. The Sun is not static. Its surface is constantly changing, marked by sunspots, solar flares, and coronal mass ejections. Sunspots are regions where strong magnetic fields inhibit convection, creating cooler, darker areas on the photosphere. They appear dark only by contrast. A sunspot is still incredibly hot, about 3,800 degrees Celsius, but that's cooler than the surrounding photosphere. Sunspots come and go in an 11-year cycle, the solar cycle, during which the sun's magnetic field reverses polarity. At solar maximum, the sun is covered with sunspots and is more active, producing more flares and coronal mass ejections. At solar minimum, the sun is quieter, with few or no sunspots. This cycle has been observed for centuries, ever since Galileo first turned his telescope toward the sun and discovered that it was not the perfect, unblemished sphere that ancient philosophy had claimed. Solar flares are sudden releases of magnetic energy, explosions on the sun's surface that release as much energy as billions of nuclear bombs. They accelerate particles to nearly the speed of light and emit intense radiation across the electromagnetic spectrum, from radio waves to X-rays and gamma rays. When a flare is directed toward Earth, it can disrupt radio communications, damage satellites, and create beautiful auroras as charged particles interact with Earth's magnetic field and atmosphere. Coronal mass ejections are even more dramatic. Enormous bubbles of plasma and magnetic field ejected from the sun's corona, carrying billions of tons of matter into space at speeds of millions of miles per hour. When a coronal mass ejection hits Earth, it can cause geomagnetic storms, disrupting power grids and communication systems, but also creating spectacular auroral displays visible at lower latitudes than usual. The solar wind is a constant stream of charged particles flowing outward from the sun's corona, filling the solar system with a tenuous plasma. This wind travels at speeds ranging from about 250 to 750 kilometers per second, carrying the sun's magnetic field with it, creating the heliosphere, a vast bubble of solar influence extending far beyond the orbit of Pluto. The solar wind shapes the magnetospheres of planets, compressing them on the sunward side and stretching them into long tails on the night side. Earth's magnetic field protects us from most of the solar wind, deflecting the charged particles and preventing them from stripping away our atmosphere. The boundary where the solar wind meets the interstellar medium, called the heliopause, is about 120 astronomical units from the Sun. Both Voyager spacecraft have crossed this boundary, entering interstellar space. Though they still remain within the Sun's gravitational influence, the Sun rotates, but not as a solid body. Because it's made of plasma, different parts rotate at different speeds, a phenomenon called differential rotation. The equator rotates faster than the poles, completing a rotation in about 25 days, compared to about 35 days at the poles. This differential rotation winds up the Sun's magnetic field, creating the complex magnetic structures that produce sunspots, flares, and coronal mass ejections. The Sun's magnetic field is generated by a dynamo process, driven by the convective motions in the outer layers and the differential rotation. Every 11 years, the magnetic field reverses, with the north and south magnetic poles switching places, though the mechanism behind this reversal is still not completely understood. Helioseismology, the study of waves traveling through the Sun, has revolutionized our understanding of the solar interior. Just as seismologists study earthquakes to learn about Earth's interior, helioseismologists study oscillations on the Sun's surface to probe its internal structure. The Sun rings like a bell, with millions of different oscillation modes, each penetrating to different depths and revealing information about temperature, density, and composition. These oscillations are caused by sound waves bouncing around inside the sun, creating patterns of motion on the surface that can be detected by measuring tiny Doppler shifts in the light from different regions. Through helioseismology, astronomers have confirmed the structure of the sun's interior, measured the rotation rate at different depths, and even detected subtle changes associated with the solar cycle. The sun is slowly getting brighter. When it first formed about 4.6 billion years ago, it was only about 70% as luminous as it is today. Over billions of years, as helium accumulates in the core, and the core contracts and heats up, the rate of fusion increases and the sun's luminosity grows. This slow brightening has profound implications for Earth's climate. In the distant past, when the sun was dimmer, Earth should have been frozen. Yet geological evidence shows that liquid water existed on the surface. This is the faint young sun paradox, and the solution likely involves a thicker atmosphere with more greenhouse gases, keeping Earth warm despite the dimmer sun. In the future, as the sun continues to brighten, Earth will become hotter, eventually too hot for liquid water to exist on the surface, though this won't happen for another billion years or so. The sun has enough hydrogen fuel to continue fusing for about another 5 billion years. When the hydrogen in the core is exhausted, the core will contract and heat up, while the outer layers expand and cool, and the sun will become a red giant, swelling to perhaps 100 times its current diameter, possibly engulfing Mercury and Venus, and rendering Earth uninhabitable. The sun will then fuse helium into carbon and oxygen in its core, a brief phase lasting only about 100 million years. Eventually, the sun will shed its outer layers, creating a planetary nebula, and the core will collapse into a white dwarf, a dense Earth-sized remnant that will slowly cool over trillions of years, eventually fading to black. But that's so far in the future that it's almost meaningless. The sun is only halfway through its main sequence lifetime, and it will continue to shine steadily for billions of years more. For thousands of years, before compasses and GPS, before maps and satellites, humans navigated by the stars. The constellations were not just patterns in the sky. They were guides, calendars, storytelling devices, connections to the divine. Different cultures or different patterns told different stories, but all recognized that the stars were fixed relative to each other, that they wheeled overhead in predictable patterns, that they could be trusted to return night after night, season after season, generation after generation. Tonight, we trace these ancient patterns, these stellar maps that guided sailors across oceans and travelers across deserts, and discover that the constellations are more than mythology. They're a testament to human curiosity, to our need to find meaning in the cosmos, to our recognition that we are part of something larger than ourselves. The constellations we recognize today in Western astronomy are largely inherited from ancient Greece and Rome, though many have roots in even older Babylonian and Egyptian star lore. The International Astronomical Union recognizes 88 official constellations, covering the entire celestial sphere, though only about half are visible from any given location on Earth. Some constellations are ancient: Orion, Ursa Major, Scorpius, mentioned in texts thousands of years old, their patterns so distinctive that multiple cultures independently recognize them. Others are more recent inventions, created by European astronomers in the 16th and 17th centuries to fill in the southern skies that were invisible from Mediterranean latitudes, or to fill gaps between the classical constellations. These newer constellations often have prosaic names: telescopium, microscopium, octans, reflecting the scientific age in which they were created, lacking the mythological grandeur of the ancient patterns. Orion the Hunter is perhaps the most recognizable constellation in the sky, visible from nearly every inhabited place on Earth. 3 bright stars form Orion's belt, a distinctive pattern that has been recognized by cultures worldwide. The ancient Egyptians associated these stars with Osiris, god of the afterlife. The ancient Chinese saw them as a bridge across the celestial river. Indigenous Australians saw them as 3 brothers in a canoe. The constellation contains some of the most spectacular objects in the night sky. Betelgeuse, the red supergiant marking Orion's shoulder, and Rigel, the blue supergiant at his foot, both among the brightest stars visible from Earth. Below the belt hangs Orion's sword, where the naked eye sees a fuzzy patch that telescopes reveal to be the Orion Nebula, a stellar nursery where new stars are being born. Orion rises in the east in late autumn, dominates the winter sky, and sets in the west by spring, a seasonal marker that has regulated human activities for millennia. Ursa Major, the Great Bear, contains the asterism known as the Big Dipper, 7 bright stars forming a shape that looks more like a ladle than a bear to modern eyes. But the ancient Greeks saw a bear, as did many Native American tribes, despite having no contact with each other. A remarkable example of convergent mythology. The 2 stars at the end of the Dipper's bowl, Dubhe and Merak, are called the pointer stars because a line drawn through them points toward Polaris, the North Star. For centuries, travelers in the Northern Hemisphere have used this trick to find north, to orient themselves, to navigate across unfamiliar terrain. The Big Dipper is circumpolar from mid-northern latitudes, meaning it never sets, instead circling around Polaris throughout the night and throughout the year. This constancy made it a reliable reference point, a celestial anchor in a changing world. Polaris, the North Star, sits almost directly above Earth's North Pole, making it appear stationary while all other stars wheel around it. This is an accident of geometry. Earth's rotation axis happens to point almost directly at Polaris, though this hasn't always been the case, and won't always be in the future. Earth's axis precesses, wobbling like a spinning top, completing one cycle every 26,000 years. 5,000 years ago, the pole star was Thuban in the constellation Draco. In about 12,000 years, it will be Vega in Lyra. But for now, for our time, Polaris marks true north, a faithful guide for navigators, a fixed point in the turning sky. The star itself is actually a supergiant, about 2,500 times more luminous than the Sun, located about 430 light-years away. It appears bright not because it's especially close, but because it's intrinsically luminous, a massive star burning through its fuel far faster than our Sun. The zodiac constellations, Aries, Taurus, Gemini, Cancer, Leo, Virgo, Libra, Scorpius, Sagittarius, Capricornus, Aquarius, Pisces, are the constellations through which the Sun appears to move over the course of a year. This apparent motion is actually due to Earth's orbit around the Sun, which causes the Sun to appear against different background stars at different times of year. The zodiac was important to ancient astronomers and astrologers because the Sun, Moon, and planets all move through these constellations, making them the stage on which celestial dramas played out. The zodiac constellations are not equally sized or equally spaced, and the Sun actually passes through a 13th constellation, Ophiuchus, though this is rarely mentioned in astrological contexts. The zodiac is a human invention, a way of dividing the sky into manageable sections, but it's based on the real geometry of the solar system, on the plane of Earth's orbit, on the paths that celestial bodies actually follow. The Southern Cross, Crux, is the smallest constellation in the sky, but one of the most distinctive and culturally important for people in the Southern Hemisphere. Its 4 bright stars form a cross shape that has been used for navigation for centuries, particularly by sailors crossing the southern oceans. The long axis of the cross points approximately toward the south celestial pole, though not as precisely as the Big Dipper points to Polaris. There's no bright south pole star, so southern navigators have had to use more complex methods to find true south. The Southern Cross appears on the flags of Australia, New Zealand, Brazil, and Papua New Guinea, among others, a symbol of southern identity and connection to the night sky. The constellation contains the Jewel Box, a beautiful open star cluster, visible to the naked eye as a hazy patch, and the Coalsack Nebula, a dark cloud of dust that blocks the light of stars behind it, appearing as a dark patch against the Milky Way. Precession of the equinoxes means that the constellations visible at a given time of year slowly change over millennia. The ancient Greeks saw the sun in Aries at the spring equinox, which is why Aries is traditionally the first sign of the zodiac. But due to precession, the sun is now in Pisces at the spring equinox, and in a few centuries, it will be in Aquarius, the dawning of the age of Aquarius that the song refers to. This slow drift means that the zodiac signs used in astrology no longer correspond to the actual positions of the sun in the constellations, a fact that astrologers handle in various ways. But from an astronomical perspective, precession is simply a consequence of Earth's wobbling axis, a predictable phenomenon that ancient astronomers like Hipparchus discovered over 2,000 years ago by comparing their observations to older records and noticing that the positions of stars relative to the equinoxes had shifted. The Milky Way itself was seen as a constellation or celestial feature by many ancient cultures. The Greeks called it the Milky Circle and told stories of it being milk spilled by the goddess Hera. The Chinese saw it as the Silver River separating two lovers. The Maori of New Zealand saw it as a canoe. We now know that the Milky Way is our view of our own galaxy from inside it, the combined light of billions of stars, too distant to resolve individually. But the ancient names and stories reflect a deep human need to explain and mythologize the sky, to make the cosmos comprehensible through narrative. Indigenous Australian astronomy is among the oldest continuous astronomical traditions in the world, stretching back over 65,000 years. Aboriginal Australians recognized not just the bright stars, but also the dark patches in the Milky Way, seeing them as constellations in their own right. The emu in the sky is formed by dark dust clouds in the Milky Way, visible as a bird-shaped silhouette stretching across the sky. Different Aboriginal groups have different constellations and different stories, but many use the stars as calendars, noting when certain stars rise or set to determine when to hunt certain animals, when to gather certain plants, when to perform certain ceremonies. This practical astronomical knowledge, passed down through oral tradition for thousands of generations, demonstrates that constellations are not just stories, they're tools, ways of organizing time and space, ways of living in harmony with natural cycles. Most stars are not alone. More than half of all stars in the galaxy exist in binary or multiple star systems, gravitationally bound to one another, orbiting a common center of mass in a cosmic dance that can last for billions of years. These stellar pairs are not accidents. They're a natural consequence of star formation, born together from the same collapsing cloud, destined to remain together for their entire lives. Tonight, we explore these binary systems, these stellar partnerships, and discover that even in the vastness of space, Even among objects as massive and powerful as stars, companionship is common, connection is fundamental, and the universe creates in pairs as often as it creates in isolation. Binary stars come in many varieties, classified by how we detect them and how they interact. Visual binaries are pairs that can be resolved as separate stars through a telescope, their orbital motion visible over years or decades of observation. Spectroscopic binaries are too close together to be resolved visually, but their orbital motion reveals itself through periodic Doppler shifts in their spectra as they move toward and away from us. Eclipsing binaries are pairs whose orbital plane is aligned with our line of sight, so that one star periodically passes in front of the other, causing regular dips in the system's brightness. And astrometric binaries are detected by the wobble they induce in their companion's motion across the sky, even when the companion itself is too faint to see directly. Each type reveals different information about the stars involved, their masses, their sizes, their orbital parameters, making binary systems invaluable laboratories for testing our understanding of stellar physics. Albireo, the star marking the head of Cygnus the Swan, is one of the most beautiful visual binaries in the sky. Through a telescope, this single point of light resolves into two stars, one golden yellow, the other sapphire blue, separated by about 35 arcseconds, an angular distance small enough that they appear as one to the naked eye, but easily split by even a small telescope. The color contrast is striking, the warm yellow of the brighter star complementing the cool blue of its fainter companion. The two stars orbit each other, though the orbital period is so long, perhaps 100,000 years, that no measurable orbital motion has been detected in the few centuries since telescopes were invented. They're separated by at least 4,400 astronomical units, over 100 times the distance from the Sun to Pluto. Yet they're gravitationally bound, partners in a dance so slow that human civilization will rise and fall many times before they complete a single orbit. Sirius, the brightest star in the night sky, is actually a binary system. The bright star we see, Sirius A, is a main sequence star about twice the mass of the Sun and 25 times more luminous. But orbiting it, invisible to the naked eye, and difficult to see even through telescopes due to the glare of Sirius A, is Sirius B, a white dwarf, the collapsed core of a star that was once more massive than Sirius A but has already exhausted its fuel and shed its outer layers. Sirius B is tiny, about the size of Earth, but incredibly dense, containing about the mass of the Sun compressed into a volume smaller than our planet. The two stars orbit each other every 50 years, their gravitational dance causing Sirius A to wobble slightly in its motion across the sky. This wobble was detected in the 19th century, leading astronomers to predict the existence of an unseen companion, which was finally observed in 1862. Sirius B was one of the first white dwarfs discovered, revealing a new phase of stellar evolution that had been previously unknown. Algol, the demon star in the constellation Perseus, is an eclipsing binary that has fascinated astronomers for centuries. Every 2.87 days, Algol's brightness drops noticeably for about 10 hours, as the dimmer companion star passes in front of the brighter primary star, blocking some of its light. This regular variation was noted by ancient astronomers, who found it eerie and ominous, hence the name Algol, from the Arabic for the demon's head. We now understand that Algol is a binary system consisting of a bright blue-white star and a dimmer orange subgiant, orbiting so close together that they're only about 6 million miles apart, less than 1/10 the distance from Earth to the Sun. The two stars are so close that material is being transferred from the subgiant to the more massive primary, creating an accretion disk and making the system even more complex and dynamic. Algol represents a phase of binary evolution where the stars are interacting, exchanging mass, influencing each other's evolution in ways that isolated stars never experience. Mizar and Alcor, the second star from the end of the Big Dipper's handle, appear as a close pair to the naked eye and were used as a vision test by ancient cultures. If you could see them as separate stars, your eyesight was considered good. But Mizar is itself a binary, and so is Alcor, and the Mizar binary components are themselves each binaries, making this a sextuple star system. 6 stars, all gravitationally bound, all orbiting a common center of mass in a complex hierarchical arrangement. The innermost binaries orbit each other in days, the next level in thousands of years, and the entire system takes millions of years to complete one full orbit. This nested structure is stable because the orbital separations are hierarchical. Each level is separated by a factor of at least 10 from the next level, preventing chaotic interactions. Mizar and Alcor demonstrate that stellar systems can be extraordinarily complex, with multiple levels of organization, yet still stable over billions of years. Binary systems allow astronomers to measure stellar masses with precision. By observing the orbital period and separation of a binary system and applying Kepler's laws of orbital motion, astronomers can calculate the combined mass of the 2 stars. If the individual motions of each star around the center of mass can be measured, the individual masses can be determined. This is the only direct way to measure stellar masses, and nearly everything we know about the relationship between a star's mass and its other properties, luminosity, temperature, lifetime, comes from studying binary systems. Without binaries, our understanding of stellar evolution would be far more limited, based on theory and indirect evidence, rather than direct measurement. Some binary systems are so close that the 2 stars actually touch, sharing a common envelope of gas. These contact binaries are egg-shaped rather than spherical, distorted by their mutual gravity and rapid rotation. The 2 stars orbit each other in just hours, whirling around their common center of mass at tremendous speeds, their surfaces nearly touching or actually merged. These systems are unstable on long timescales. They're losing energy through gravitational radiation and will eventually merge into a single star. But the merger process can take millions or billions of years, and in the meantime, these contact binaries represent an extreme form of stellar interaction, a reminder that stars are not rigid objects, but fluid, dynamic, responsive to the gravitational forces acting on them. Cataclysmic variables are binary systems where a white dwarf is accreting matter from a companion star, usually a red dwarf or subgiant. The material from the companion forms an accretion disk around the white dwarf, spiraling inward and heating up through friction until it's hot enough to emit X-rays. Periodically, the accumulated material on the white dwarf's surface reaches a critical density and temperature, triggering a thermonuclear explosion that causes the system to brighten dramatically. A nova. These novae can increase the system's brightness by a factor of 100,000 or more, making stars that are normally too faint to see with the naked eye suddenly visible, appearing as new stars in the sky, hence the name nova from the Latin for new. The explosion doesn't destroy the white dwarf, it just blows off the accumulated material, and the accretion process begins again, leading to recurrent novae that erupt every few decades or centuries. Type Ia supernovae, the explosions used as standard candles to measure cosmic distances and discover dark energy, are thought to occur in binary systems where a white dwarf accretes matter from a companion until it reaches a critical mass, about 1.4 times the mass of the Sun, the Chandrasekhar limit. At this mass, the white dwarf can no longer support itself against gravity, and it collapses, triggering a runaway thermonuclear explosion that completely destroys the star, leaving no remnant behind. Because all Type 1 supernovae involve white dwarfs reaching the same critical mass, they all have similar peak luminosities, making them useful for measuring distances to distant galaxies. These supernovae are so bright they can outshine entire galaxies for weeks, and they're visible across billions of light years, making them invaluable tools for cosmology. Stars are not immortal. They're born, they live, and they die, and the process of stellar evolution transforms them in profound ways. When a star like our Sun exhausts the hydrogen fuel in its core, it doesn't simply fade away, it transforms, swelling into a red giant, a star so large that it could swallow the inner planets of its solar system, yet so cool that its surface glows a deep, ruddy red. These red giants are the elderly stars of the galaxy, approaching the end of their lives, yet they're among the most beautiful objects in the night sky, glowing with a soft, warm light that speaks of age and transformation. Tonight, we explore these quiet giants, these evolved stars, and discover that stellar death is not an ending, but a transformation, a final act of creation before the curtain falls. Red giants form when a star exhausts the hydrogen in its core. For billions of years, the star has been fusing hydrogen into helium, maintaining a balance between the outward pressure from fusion and the inward pull of gravity. But eventually, the hydrogen runs out, and fusion in the core stops. Without the outward pressure to support it, the core contracts under its own gravity, and as it contracts, it heats up. This heat causes the hydrogen in a shell surrounding the core to begin fusing, and the energy from this shell fusion is so intense that it pushes the star's outer layers outward. The star expands, growing to tens or hundreds of times its original size, while its surface cools, giving it the characteristic red color. The transformation from main sequence star to red giant takes only a few million years, a brief transition in the star's multi-billion-year lifetime. Arcturus, the brightest star in the constellation Boötes and the fourth brightest star in the night sky, is a red giant about 25 times larger than the Sun and about 170 times more luminous. Its surface temperature is only about 4,300 degrees Celsius, cooler than the Sun, but its enormous size more than compensates, making it far more luminous overall. Arcturus is in the later stages of its life, having already exhausted the hydrogen in its core, and now fusing helium into carbon and oxygen. The star is also moving rapidly through the galaxy, part of a stream of old stars that may have once belonged to a dwarf galaxy that was consumed by the Milky Way billions of years ago. Arcturus is a visitor, passing through our neighborhood on a trajectory that will eventually carry it far from the Sun, a reminder that stars are not fixed but are in constant motion, following orbits through the galaxy that can bring them together and pull them apart over cosmic timescales. Aldebaran, the orange eye of Taurus the bull, is another red giant, about 44 times larger than the Sun and about 150 times more luminous. It's closer than Arcturus, only about 65 light-years away, making it appear brighter despite being intrinsically less luminous. Aldebaran is surrounded by the Hyades star cluster, though it's not actually a member. It's a foreground star that happens to lie in the same direction, creating the illusion of association. The star is in the early stages of red giant evolution, still fusing hydrogen in a shell around its inert helium core. Eventually, the core will become hot and dense enough to ignite helium fusion, and Aldebaran will enter a new phase of evolution, becoming even more luminous, before eventually shedding its outer layers and collapsing into a white dwarf, Betelgeuse. The red supergiant marking Orion's shoulder is one of the largest stars visible to the naked eye, with a radius about 900 times that of the Sun. If placed at the center of our solar system, Betelgeuse would extend past the orbit of Mars, possibly even reaching Jupiter. The star is so large that its surface gravity is incredibly weak. The outer layers are barely held to the star, and Betelgeuse is losing mass through a powerful stellar wind, shedding material into space at a rate of about 1 Earth mass every 10,000 years. The star is also variable, changing in brightness over periods of months and years as it pulsates, expanding and contracting, its surface rising and falling like a slow tide. Betelgeuse is nearing the end of its life and could explode as a supernova at any time, though any time in astronomical terms could mean tomorrow or 100,000 years from now. When it does explode, it will be visible in daylight for weeks and will be one of the most spectacular astronomical events in human history. The helium flash is a dramatic event that occurs in the cores of low-mass red giants when helium fusion finally ignites. For millions of years, the helium core has been contracting and heating up, supported not by thermal pressure, but by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being compressed beyond a certain density. When the temperature reaches about 100 million degrees Celsius, helium fusion ignites explosively, releasing enormous amounts of energy in a matter of seconds. But because the core is degenerate, this energy doesn't cause the core to expand and cool as it would in a normal star. Instead, the temperature rises even further, causing the fusion rate to skyrocket in a runaway process. Within minutes, the core heats up enough to lift the degeneracy. The core expands, the temperature drops, and the fusion rate stabilizes. The helium flash is invisible from outside the star. The energy is absorbed by the overlying layers and doesn't reach the surface, but it marks a crucial transition in the star's evolution. From a star fusing hydrogen in a shell to a star fusing helium in its core. Mira, a red giant in the constellation Cetus, is the prototype of a class of variable stars called Mira variables. These are evolved red giants that pulsate with periods of months to years, changing in brightness by factors of 100 or more. Mira itself varies from magnitude 2, easily visible to the naked eye, to magnitude 10, requiring a telescope to see, over a period of about 332 days. The pulsations are driven by instabilities in the star's outer layers. The star expands, cools, and becomes more opaque, trapping radiation and causing further expansion, until it becomes so extended that it cools dramatically and contracts again, starting the cycle over. Mira is also losing mass rapidly, surrounded by a vast envelope of gas that it has shed over thousands of years, visible in ultraviolet images as a comet-like tail stretching across several light years, created by the star's motion through the interstellar medium. Planetary nebulae are the final act of stars like the Sun, the beautiful shells of gas ejected when a red giant sheds its outer layers. Despite the name, they have nothing to do with planets. They were named by 18th century astronomers who thought they looked like the disks of planets through their small telescopes. A planetary nebula forms when a red giant's outer layers become so extended and tenuous that they're no longer gravitationally bound to the core, Stellar winds and radiation pressure push these layers into space, creating an expanding shell of gas that's illuminated by ultraviolet radiation from the hot core, the future white dwarf at the center. The nebulae are often strikingly beautiful, with complex shapes, rings, spirals, bipolar lobes, created by magnetic fields, rotation, and binary companions. They're also brief, lasting only a few tens of thousands of years before dispersing into the interstellar medium, enriching it with the heavy elements created in the star's core. The Ring Nebula in Lyra is one of the most famous planetary nebulae, visible through small telescopes as a ghostly smoke ring in the sky. The ring is actually a cylinder of gas viewed end-on, with the hot white dwarf at the center, barely visible as a faint point of light. The nebula is expanding at about 20 kilometers per second, and it's about 2,000 years old, meaning it was ejected around the time of the Roman Empire. The gas is glowing because it's being ionized by ultraviolet radiation from the central white dwarf, which has a surface temperature of about 100,000 degrees Celsius. Different elements emit different colors. Hydrogen emits red, oxygen emits green and blue. Nitrogen emits red, creating the multicolored appearance visible in photographs. The Ring Nebula is a preview of the Sun's fate, a glimpse of what our solar system will look like in about 5 billion years, when the Sun becomes a red giant and then sheds its outer layers. The universe began with only hydrogen and helium, the simplest elements, created in the first few minutes after the Big Bang. Everything else, carbon, oxygen, nitrogen, iron, calcium, all the elements that make up planets and life, was created later, in the cores of stars and in the explosions of supernovae. You are made of stardust, not metaphorically but literally. Every atom in your body heavier than hydrogen was forged in a star, created through nuclear fusion in stellar cores or through the intense conditions of supernova explosions, then dispersed into space to be incorporated into new stars, new planets, new life. Tonight we explore this cosmic alchemy, this process by which stars transform simple elements into complex ones, and discover that we are intimately connected to the stars, that our very existence depends on stellar death and rebirth. Nuclear fusion in stellar cores creates heavier elements from lighter ones. In main sequence stars like the Sun, hydrogen fuses into helium through the proton-proton chain or the CNO cycle. When the hydrogen is exhausted and the star becomes a red giant, helium fuses into carbon and oxygen through the triple alpha process, where 3 helium nuclei combine to form carbon. And then carbon captures another helium nucleus to form oxygen. In more massive stars, the process continues. Carbon fuses into neon and magnesium, neon into oxygen and magnesium, oxygen into silicon and sulfur, and finally, silicon into iron. Each stage of fusion requires higher temperatures and densities than the last, and each stage lasts for a shorter time. A massive star might fuse hydrogen for millions of years, helium for hundreds of thousands of years, carbon for hundreds of years, and silicon for just a few days, before the core is converted to iron. The fusion process releases energy because the products of fusion are slightly less massive than the reactants. The missing mass is converted to energy according to Einstein's equation E to mc quadrime. This mass deficit, called the binding energy, is what powers stars and what makes fusion possible. Elements up to iron can be created through fusion with a net release of energy, but iron is special. It has the highest binding energy per nucleon of any element, meaning it's the most stable nucleus. Fusing iron into heavier elements requires energy rather than releasing it, which is why fusion stops at iron in stellar cores. This is a fundamental limit imposed by nuclear physics, a boundary that determines the fate of massive stars. Iron is the end of the line for fusion. Fusing elements lighter than iron releases energy, but fusing iron requires energy. It's endothermic rather than exothermic. This means that once a massive star's core is converted to iron, no further fusion can occur, and the core has no way to support itself against gravity. The core collapses catastrophically, falling inward at speeds approaching a quarter of the speed of light, and in less than a second, it compresses from the size of Earth to the size of a city, forming a neutron star or black hole. The collapse releases an enormous amount of gravitational energy, which drives a shockwave outward through the star's outer layers, blowing them into space in a supernova explosion. The explosion is so energetic that it briefly outshines an entire galaxy, releasing as much energy in a few weeks as the Sun will emit over its entire 10 billion-year lifetime. The core collapse process is extraordinarily violent. As the iron core implodes, electrons are forced into protons, creating neutrons and releasing neutrinos in a process called neutronization. The neutrinos carry away most of the energy from the collapse. About 99% of the total energy released goes into neutrinos, which stream out of the core at nearly the speed of light. Only about 1% of the energy goes into the kinetic energy of the explosion and the light we see. But even this small fraction is enough to blow the star apart. The neutrino burst from a nearby supernova would be detectable on Earth. In fact, neutrinos from supernova 1987A were detected by neutrino observatories, arriving hours before the light because they escaped from the core immediately, while the light had to work its way through the star's outer layers. Supernovae create elements heavier than iron through a process called rapid neutron capture, or the R process. During the explosion, the intense neutron flux allows atomic nuclei to capture neutrons faster than they can decay, building up heavy elements like gold, platinum, uranium, and thorium. These elements cannot be created through normal fusion. They require the extreme conditions of a supernova or neutron star merger. Every gold atom in every piece of jewelry, every uranium atom in every nuclear reactor was created in a supernova explosion or neutron star collision, forged in conditions of unimaginable temperature and density, then scattered into space to eventually be incorporated into new star systems. The gold in your wedding ring is stardust from a supernova that exploded billions of years ago, before the Sun even existed. Neutron star mergers, discovered through gravitational wave observations in 2017, are another site of our process, nucleosynthesis. When two neutron stars spiral together and merge, they create conditions even more extreme than a supernova, with enormous densities and neutron fluxes that are ideal for creating the heaviest elements. The merger detected in 2017, designated GW170817, was observed in gravitational waves by LIGO and Virgo, and also in electromagnetic radiation across the spectrum, from gamma rays to radio waves. Analysis of the light from the merger showed clear signatures of heavy element production, confirming that neutron star mergers are a major source of gold, platinum, and other heavy elements in the universe. The merger produced an estimated 10 Earth masses of gold and platinum scattered into space to enrich future generations of stars and planets. The Crab Nebula is the remnant of a supernova that was observed by Chinese and Arab astronomers in 1054 CE. For weeks, the supernova was visible in daylight, appearing as a bright new star in the constellation Taurus. Nearly 1,000 years later, we can see the expanding cloud of gas and dust created by the explosion, now spanning about 11 light years and still expanding at about 1,500 kilometers per second. At the center of the nebula is a pulsar, a rapidly rotating neutron star that emits beams of radiation like a cosmic lighthouse, spinning 30 times per second. The nebula is glowing because it's being energized by the pulsar's magnetic field, which accelerates particles to nearly the speed of light, creating a wind of relativistic particles that illuminates the surrounding gas. The Crab Nebula is a laboratory for studying supernova remnants, neutron stars, and the acceleration of cosmic rays. And it's a reminder that stellar death is not an ending, but a transformation, creating new structures and enriching the interstellar medium with heavy elements. Type 2 supernovae occur when massive stars, those with more than about 8 times the mass of the Sun, exhaust their nuclear fuel and undergo core collapse. Type E supernovae, as we discussed earlier, occur in binary systems when a white dwarf accretes matter and reaches the Chandrasekhar limit. Both types enrich the interstellar medium with heavy elements, but they produce different mixtures. Type 2 supernovae produce more oxygen, neon, and magnesium, while Type 1a supernovae produce more iron, nickel, and chromium. The combination of both types, occurring over billions of years, has gradually enriched the galaxy with heavy elements, transforming it from the simple hydrogen and helium mixture of the early universe into the chemically complex environment we see today. The Sun and Solar System formed from a molecular cloud that had been enriched by previous generations of stars. The heavy elements in that cloud, the carbon, oxygen, silicon, iron, came from supernovae that exploded billions of years earlier. When the cloud collapsed to form the Sun and planets, these heavy elements were incorporated into the new system. The rocky planets, Mercury, Venus, Earth, Mars, are made primarily of silicon, oxygen, iron, and other heavy elements. Earth's iron core, its rocky mantle, its oceans and atmosphere, all contain elements created in stars. And life, which depends on carbon, oxygen, nitrogen, phosphorus, and other heavy elements, is built entirely from stardust, from atoms forged in stellar cores and supernova explosions. The calcium in your bones was created in a supernova explosion, fused from lighter elements in the intense heat of the blast. The iron in your blood, essential for carrying oxygen, was created in the core of a massive star and dispersed by a supernova. The oxygen you breathe was created through helium fusion in red giant stars. The carbon that forms the backbone of every organic molecule in your body was created through the triple alpha process in the cores of dying stars. You are, quite literally, made of star stuff, assembled from atoms that have cosmic histories stretching back billions of years, that have been through multiple cycles of stellar birth and death, that carry within them the memory of the universe's chemical evolution. Supernova 1987A, which exploded in the Large Magellanic Cloud, was the nearest supernova visible to the naked eye since Kepler's supernova in 1604. Astronomers were able to study it in unprecedented detail, observing the shockwave as it plowed through the surrounding gas, detecting neutrinos from the core collapse, and watching as radioactive elements created in the explosion decayed and powered the light curve. The supernova confirmed many theoretical predictions about how massive stars die and provided new insights into the explosion mechanism. Decades later, the expanding remnant is still being studied, revealing new details about the structure of the progenitor star and the physics of supernova explosions. The remnant is now colliding with a ring of material ejected by the progenitor star thousands of years before the explosion, creating hot spots that glow in X-rays and visible light, a cosmic laboratory for studying shock physics and particle acceleration. When a massive star explodes as a supernova, the core that remains is compressed to extraordinary density, forming a neutron star, an object containing more mass than the Sun compressed into a sphere only about 20 kilometers across. The density is so extreme that a teaspoon of neutron star material would weigh about 1 billion tons on Earth. These neutron stars often rotate rapidly, spinning dozens or even hundreds of times per second. And if their magnetic field is aligned properly, they emit beams of radiation that sweep across space like a lighthouse beam. When one of these beams points toward Earth, we detect a pulse of radiation, regular as clockwork, and we call the object a pulsar. Tonight, we explore these cosmic clocks, these remnants of stellar death that pulse with such precision they rival atomic clocks, and discover that even in death, stars can create order, can maintain rhythm, can mark time with extraordinary accuracy. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, then a graduate student at Cambridge University. She noticed a strange signal in her radio telescope data, a series of pulses occurring every 1.337 seconds with remarkable regularity. The signal was so regular that it was briefly considered as a possible transmission from an extraterrestrial civilization and was jokingly labeled LGM, 1 for little green men. But further observations revealed more pulsars with different periods, and it soon became clear that these were natural phenomena, not artificial signals. The explanation, rapidly rotating neutron stars with strong magnetic fields, was proposed shortly after the discovery and has been confirmed by decades of subsequent observations. Bell Burnell's discovery opened a new window on the universe and revealed a new class of objects that had been predicted theoretically but never observed. Pulsars rotate incredibly fast because of conservation of angular momentum. When the core of a massive star collapses from a radius of thousands of kilometers to a radius of just 10 or 20 kilometers, its rotation rate increases dramatically, just as a figure skater spins faster when pulling in their arms. A star that was rotating once every few weeks before collapse might rotate dozens of times per second afterward. The fastest known pulsar, PSR Jones 748, 2446 AD, rotates 716 times per second. Its equator is moving at about 24% of the speed of light, approaching the theoretical maximum rotation rate for a neutron star. Any faster, and centrifugal forces would overcome gravity and tear the star apart. The structure of a neutron star is unlike anything else in the universe. The outer layer, the crust, is a solid lattice of atomic nuclei embedded in a sea of electrons, similar to ordinary matter, but compressed to densities millions of times greater than anything on Earth. Below the crust lies the outer core, where neutrons are so densely packed that they form a superfluid, a quantum fluid, with zero viscosity that flows without friction. Deeper still is the inner core, where the density becomes so extreme that we're not sure what form matter takes. It might be a soup of quarks, the fundamental particles that make up neutrons and protons, or it might be some exotic form of matter we've never encountered. Neutron stars are laboratories for studying matter at densities that can never be recreated on Earth, and they challenge our understanding of nuclear physics and quantum mechanics. The magnetic field of a neutron star is also extraordinarily strong, typically about 1 trillion times stronger than Earth's magnetic field. This intense magnetic field is created by the compression of the original star's magnetic field during core collapse. The same field that was spread over thousands of kilometers is now concentrated into a sphere, 20 kilometers, across, amplifying its strength enormously. The magnetic field accelerates charged particles to nearly the speed of light, creating beams of radiation that emerge from the magnetic poles. If the magnetic axis is tilted relative to the rotation axis, these beams sweep around as the neutron star rotates, creating the pulses we detect. The mechanism is similar to a lighthouse. The light is always on, but we only see it when the beam points toward us. The Crab pulsar at the center of the Crab Nebula rotates 30 times per second and emits pulses across the electromagnetic spectrum, from radio waves to gamma rays. The pulsar is gradually slowing down, losing rotational energy at a rate of about 5 billion watts. This energy goes into accelerating particles and powering the nebula's glow. The slowdown is measurable. The pulsar's period is increasing by about 38 nanoseconds per day, a tiny amount, but detectable with modern instruments. By measuring this slowdown, astronomers can calculate the pulsar's age, which matches the age of the supernova remnant, confirming that the pulsar was created in the 1054 supernova explosion. The Crab pulsar is one of the few pulsars visible at optical wavelengths, appearing as a faint star that blinks on and off 30 times per second, a cosmic strobe light in the heart of the nebula. Millisecond pulsars are a special class of pulsars that rotate hundreds of times per second, far faster than typical young pulsars. These objects are thought to be old neutron stars that have been spun up by accreting matter from a binary companion. As matter from the companion spirals onto the neutron star, it carries angular momentum, gradually increasing the neutron star's rotation rate. Once the accretion stops, perhaps because the companion has been completely consumed or has moved away, the neutron star is left spinning at millisecond periods. These recycled pulsars are incredibly stable rotators, their periods changing so slowly that they rival atomic clocks in precision. Some millisecond pulsars have been timed for decades, and their pulses arrive with such regularity that they can be used to test general relativity and search for gravitational waves. The Hulse-Taylor binary pulsar, discovered in 1974, consists of a pulsar in orbit with another neutron star. The orbital period is about 7.75 hours, and the orbit is highly elliptical, bringing the two neutron stars as close as 1.1 solar radii at periastron. This system provided the first indirect evidence for gravitational waves. According to general relativity, two massive objects orbiting each other should emit gravitational waves, losing energy and causing the orbit to gradually shrink. Hulse and Taylor measured the orbital period over many years and found that it was decreasing at exactly the rate predicted by general relativity for gravitational wave emission. This discovery earned them the Nobel Prize in Physics in 1993 and confirmed a key prediction of Einstein's theory. The two neutron stars are gradually spiraling together and will eventually merge in about 300 million years, creating a more massive neutron star or possibly a black hole, and releasing a burst of gravitational waves. Magnetars are neutron stars with magnetic fields even stronger than typical pulsars, up to 1,000 times stronger, reaching quadrillions of times Earth's magnetic field. These extreme magnetic fields make magnetars the most magnetic objects known in the universe. The fields are so strong that they distort the neutron star's crust, causing starquakes that release enormous bursts of X-rays and gamma rays. Magnetars are relatively rare. Only a few dozen are known, and they're thought to form from the most massive progenitor stars, which have the strongest magnetic fields before collapse. The magnetic field energy in a magnetar is so great that it dominates over the rotational energy, unlike in normal pulsars, where rotation is the primary energy source. Magnetars occasionally produce giant flares, brief but incredibly intense bursts of gamma rays that can be detected across the galaxy. Pulsar timing arrays use networks of millisecond pulsars spread across the sky as a galaxy-sized gravitational wave detector. Gravitational waves passing through the galaxy would cause tiny changes in the distances between Earth and the pulsars, which would show up as correlated timing residuals in the pulsar signals. By monitoring dozens of pulsars for years or decades, astronomers hope to detect gravitational waves from supermassive black hole binaries in distant galaxies. Waves with periods of months to years that are too long for ground-based detectors like LIGO to observe. Recent results suggest that the first detections may be imminent, opening a new window on the universe and revealing the population of merging supermassive black holes. The detection would confirm another prediction of general relativity and provide insights into galaxy mergers and the growth of supermassive black holes. Glitches are sudden increases in a pulsar's rotation rate, caused by starquakes in the neutron star's crust or by interactions between the crust and the superfluid interior. The pulsar's rotation gradually slows due to magnetic braking, but occasionally the crust cracks and settles into a slightly smaller radius, causing the rotation rate to suddenly increase, like a figure skater pulling in their arms. The glitch is followed by a gradual relaxation as the interior and crust recouple. Studying glitches provides information about the interior structure of neutron stars, about the properties of matter at extreme densities, about the coupling between the crust and the superfluid core. The Vela pulsar is particularly prone to glitches, experiencing one every few years, making it an ideal laboratory for studying this phenomenon. On a clear, dark night, far from city lights, you can see a band of light stretching across the sky, the Milky Way, our view of our own galaxy from inside it. This faint glow is the combined light of billions of stars too distant to resolve individually, a river of starlight flowing across the heavens. Our galaxy contains somewhere between 100 and 400 billion stars, each one a sun in its own right, many with their own planetary systems, all orbiting the galactic center in a vast, slow dance that takes hundreds of millions of years to complete. Tonight, we explore our galactic home, mapping the billions of stars that surround us, and discover that we live in a vast stellar city, a cosmic metropolis where stars are our neighbors, separated by light years, but connected by gravity and shared history. The Milky Way is a barred spiral galaxy with a central bar-shaped structure surrounded by spiral arms that wind outward from the ends of the bar. Our solar system is located in a minor spiral arm called the Orion Arm or Orion Spur, about 26,000 light-years from the galactic center. We're in the galactic suburbs, far from the crowded core where stars are packed densely and the supermassive black hole lurks, but also far from the sparse outer regions where stars are few and far between. Our location is relatively safe, quiet, stable, a good place for a planetary system to evolve undisturbed for billions of years, allowing complex life to develop. The Sun orbits the galactic center at about 515,000 miles per hour, yet it takes about 225 to 250 million years to complete one orbit, a galactic year. The last time the Sun was in its current position, dinosaurs were just beginning to emerge on Earth. The galactic center, hidden from our view by intervening dust clouds, is a region of intense activity and extreme conditions. At its very heart lies Sagittarius A, a supermassive black hole with a mass of about 4.1 million times that of our Sun. Stars near the galactic center are packed so densely that the night sky on a planet in that region would be ablaze with stars, thousands of them bright enough to cast shadows. But the radiation, the gravitational interactions, the sheer chaos of that environment would make life as we know it unlikely. Astronomers have tracked individual stars orbiting Sagittarius A, watching them whip around the black hole at speeds reaching a significant fraction of the speed of light. Their orbits providing precise measurements of the black hole's mass and confirming the predictions of general relativity in the strong field regime. One star, designated S2, completes an orbit around Sagittarius A in just 16 years, approaching to within 17 light hours of the event horizon at its closest approach. The Gaia Space Telescope, launched by the European Space Agency, is creating the most detailed three-dimensional map of the Milky Way ever made. Gaia has measured the positions, distances, and motions of over 1 billion stars, about 1% of all the stars in the galaxy. This data is revolutionizing our understanding of the Milky Way's structure, revealing streams of stars from disrupted dwarf galaxies, mapping the spiral arms, measuring the galaxy's rotation, and discovering thousands of new stellar systems. The precision of Gaia's measurements is extraordinary. It can measure the position of a star to within a few millionths of an arcsecond, equivalent to measuring the width of a human hair from 1,000 kilometers away. This precision allows astronomers to trace the orbits of stars backward and forward in time, to identify stars that were born together in the same cluster but have since dispersed, to map the history of the galaxy written in the motions of its stars. The disk of the Milky Way is thin, only about 1,000 light-years thick, but 100,000 light-years across, giving it a shape like a dinner plate. Most of the galaxy's stars are in the disk, organized into spiral arms where star formation is ongoing. The spiral arms are not fixed structures, but density waves, regions where stars and gas are temporarily compressed as they orbit the galactic center. Stars move into and out of the spiral arms over millions of years, like cars entering and leaving a traffic jam. The arms appear bright because the compression triggers star formation, and young, massive stars are extremely luminous, lighting up the regions where they're born. Our Sun is currently between spiral arms in a relatively quiet region, though it passes through a spiral arm every few 100 million years as it orbits the galactic center. Some scientists have speculated that passages through spiral arms might trigger increased comet impacts on Earth, though this remains controversial. The major spiral arms of the Milky Way, the Perseus arm, the Scutum Centaurus arm, and the Sagittarius arm, are traced by concentrations of young, hot stars and regions of active star formation. The Orion arm, where we reside, is a smaller structure, sometimes called a spur or bridge, connecting the larger arms. Radio observations of hydrogen gas and infrared observations that can penetrate dust have mapped these spiral arms, revealing the galaxy's grand design structure. The spiral pattern is thought to be maintained by density waves, gravitational disturbances that propagate through the disk like ripples on a pond, compressing gas and triggering star formation as they pass. The galactic halo surrounds the disk, a roughly spherical region containing old stars, organized into globular clusters, and a diffuse population of individual stars. The halo also contains most of the galaxy's dark matter, invisible but detectable through its gravitational effects. The globular clusters in the halo are among the oldest objects in the galaxy, containing stars over 12 billion years old, formed when the Milky Way was just beginning to assemble. These clusters orbit the galactic center on elongated paths that take them far above and below the disk, and they're relics from the early universe, survivors that have outlasted countless generations of younger stars. Studying globular clusters provides insights into the early history of the galaxy, into the conditions in the young universe, into the process by which galaxies form and evolve. Some globular clusters contain hundreds of thousands of stars packed into regions only a few dozen light-years across, creating stellar densities thousands of times greater than in the solar neighborhood. The Milky Way is not isolated. It's part of the local group, a collection of about 80 galaxies dominated by the Milky Way and Andromeda. Most of the other galaxies in the local group are dwarf galaxies, small systems containing millions or billions of stars rather than the hundreds of billions in the Milky Way. Many of these dwarf galaxies are satellites of the Milky Way, orbiting our galaxy and gradually being torn apart by tidal forces. The Sagittarius dwarf elliptical galaxy is currently passing through the Milky Way's disk, being stretched into a long stream of stars that wraps around the galaxy. The Magellanic Clouds, visible from the southern hemisphere as two fuzzy patches in the sky, are dwarf irregular galaxies orbiting the Milky Way, close enough that they're interacting gravitationally with streams of gas connecting them to our galaxy. The Large Magellanic Cloud contains about 30 billion stars, the Small Magellanic Cloud about 3 billion, making them substantial galaxies in their own right, despite being dwarfed by the Milky Way. The stellar populations of the Milky Way reveal its history. Population I stars are young metal-rich stars found in the disk, formed from gas that has been enriched by previous generations of stars. Population II stars are old, metal-poor stars found in the halo and globular clusters, formed in the early universe when heavy elements were rare. The Sun is a population I star, containing about 2% heavy elements by mass, a composition that reflects billions of years of chemical enrichment. The oldest stars in the galaxy contain less than 0.01% heavy elements, formed from gas that was nearly pristine, containing only the hydrogen and helium created in the Big Bang, plus trace amounts of lithium. By studying the chemical compositions of stars, astronomers can trace the galaxy's chemical evolution, can identify stars that formed at different times and in different environments, can piece together the history of star formation and element production over billions of years. The rotation curve of the Milky Way, a plot of orbital velocity versus distance from the galactic center, reveals the presence of dark matter. In the inner galaxy, the rotation curve rises as expected from the visible matter, but in the outer galaxy, it flattens rather than declining as it should, if only visible matter were present. This flat rotation curve indicates that there's additional mass in the outer galaxy, mass that doesn't emit light, dark matter. The dark matter halo extends far beyond the visible disk, containing perhaps 10 times as much mass as all the visible stars and gas combined. This dark matter provides the gravitational scaffolding that holds the galaxy together, preventing the outer stars from flying off into space despite their high orbital velocities. The nature of dark matter remains one of the greatest mysteries in physics. It doesn't interact with light, doesn't absorb or emit radiation, and can only be detected through its gravitational effects. The Milky Way has been growing through mergers and accretion throughout its history. Streams of stars discovered by Gaia reveal the remnants of dwarf galaxies that were consumed by the Milky Way billions of years ago. The most recent major merger occurred about 10 billion years ago, when a dwarf galaxy called Gaia Enceladus collided with the Milky Way, contributing stars to the halo and possibly triggering a burst of star formation in the disk. The Milky Way continues to accrete smaller galaxies today, gradually growing in mass as it consumes its satellites. In about 4.5 billion years, the Milky Way will merge with Andromeda, creating a giant elliptical galaxy that astronomers have nicknamed Milkomeda. This merger will dramatically reshape both galaxies, but individual stars are so far apart that actual collisions between stars will be extremely rare. Stars are not eternal. They're born, they live, and they die, and the timescales involved are so vast that they seem eternal from a human perspective. But they're not. The universe is 13.8 billion years old, and the longest-lived stars, the smallest red dwarfs, can shine for trillions of years, far longer than the current age of the universe. But eventually, even these patient stars will exhaust their fuel, will fade to darkness, will join the growing population of stellar remnants that will dominate the universe in the far future. Tonight, we contemplate the future of the stars, the slow transformation of the cosmos from a place of light to a place of darkness, and discover that even in this distant future, there is a kind of peace, a reminder that all things change, that nothing lasts forever, that the universe is patient beyond measure. The Sun has about 5 billion years left on the main sequence, fusing hydrogen into helium in its core, shining steadily as it has for the past 4.6 billion years. When the hydrogen runs out, the Sun will become a red giant, swelling to perhaps 100 times its current diameter, possibly engulfing Mercury and Venus, certainly rendering Earth uninhabitable. The oceans will boil away, the atmosphere will be stripped, and the surface will be scorched to a lifeless desert. The Sun will fuse helium into carbon and oxygen in its core for about 100 million years, then shed its outer layers, creating a planetary nebula, and the core will collapse into a white dwarf, a dense, Earth-sized remnant that will slowly cool over trillions of years. This is the fate of all stars like the Sun, the inevitable end of main sequence evolution for low and medium mass stars. The white dwarf that was once our Sun will continue to orbit the galactic center, a cooling ember carrying the memory of a star that once supported life. More massive stars have shorter lives, but more dramatic deaths. A star 10 times the mass of the Sun will live for only about 20 million years before exhausting its fuel and exploding as a supernova, leaving behind a neutron star or black hole. A star 100 times the mass of the Sun might live for only a few million years, burning through its fuel at a prodigious rate, shining brilliantly but briefly before collapsing. The most massive stars are cosmic sprinters, living fast and dying young, while the smallest stars are marathon runners, burning their fuel so slowly that they'll outlive every other type of star by factors of thousands or millions. This inverse relationship between mass and lifetime means that the universe is gradually losing its most massive stars, while accumulating more and more low-mass stars and stellar remnants. Red dwarf stars, the smallest and coolest main sequence stars, are the universe's survivors. With masses between about 8% and 50% of the Sun's mass, they burn their hydrogen fuel so slowly that even the oldest red dwarfs, formed in the early universe over 13 billion years ago, are still on the main sequence, still fusing hydrogen, still shining. The smallest red dwarfs will continue to shine for trillions of years, far longer than the current age of the universe, outliving every other type of star. When the universe is 100 trillion years old, when all the massive stars have died, when all the sun-like stars have become white dwarfs, the red dwarfs will still be shining, the last lights in an increasingly dark universe. These stars are so efficient at mixing their fuel that they can use nearly all of their hydrogen, not just the core, extending their lifetimes even further. White dwarfs are the most common stellar remnants, the fate of all stars with initial masses less than about 8 times the Sun's mass. They're incredibly dense. A teaspoon of white dwarf material would weigh several tons, and they're hot when first formed, with surface temperatures that can exceed 100,000 degrees Celsius. But white dwarfs have no internal energy source. They're no longer fusing elements, so they simply radiate away their stored heat, slowly cooling over billions of years. As they cool, they change color, from blue-white to yellow to red, eventually becoming black dwarfs, cold, dark, invisible remnants. But the universe is not yet old enough for any black dwarfs to exist. Even the oldest white dwarfs, formed billions of years ago, are still warm enough to glow faintly. The first black dwarfs won't appear for many billions of years, when the universe is far older than it is now. Some white dwarfs cool so slowly that they crystallize, their carbon and oxygen atoms forming a giant cosmic diamond, a stellar jewel invisible in the darkness. Neutron stars and black holes are the remnants of the most massive stars, created in supernova explosions or direct collapse. Neutron stars will persist essentially forever, slowly cooling and slowing their rotation, but never truly dying. Black holes are even more eternal. They can't cool, can't radiate away their mass through normal processes, can only grow by accreting matter or merging with other black holes. But even black holes are not truly eternal. Stephen Hawking showed that black holes can evaporate through a quantum process now called Hawking radiation, slowly losing mass and eventually disappearing in a final burst of energy. But the timescale for this evaporation is enormous. A stellar mass black hole will take about 10 circumflex 67 years to evaporate. A supermassive black hole about 10 circumflex 100 years. These numbers are so large, they're almost meaningless, but they represent the ultimate fate of all black holes, the final dissolution of the last massive objects in the universe. The far future of the universe is a place of darkness and cold. In about 100 trillion years, star formation will have ceased as galaxies exhaust their gas supplies. The last stars will burn out, the last white dwarfs will cool to black dwarfs, and the universe will enter the degenerate era, filled with stellar remnants, but no living stars. The only light will come from occasional collisions between brown dwarfs or white dwarfs, brief flashes in the darkness. Over even longer timescales, protons may decay if certain theories of physics are correct, causing even white dwarfs and neutron stars to slowly disintegrate. And eventually, after 10 circumflex 100 years or more, even the black holes will evaporate, leaving a universe filled with nothing but photons, neutrinos, and the faintest possible quantum fluctuations. This final state, sometimes called the heat death of the universe, is a state of maximum entropy, where no gradients exist, no processes can occur, and nothing can happen. The timeline of stellar evolution extends far beyond human comprehension. The Stelliferous era, the current age when stars are actively forming and shining, began about 100 million years after the Big Bang and will last for about 100 trillion years, 1,000 times longer than the current age of the universe. We're living in the early stages of this era, when star formation is still robust, when galaxies are still rich in gas, when the universe is still actively creating new stars. The peak of star formation actually occurred about 10 billion years ago, and we're now in a slow decline, with star formation rates gradually decreasing as galaxies consume their gas supplies. But the decline is so gradual that it will take trillions of years for star formation to cease entirely. Yet there's something peaceful about contemplating these vast timescales, these ultimate fates. The universe is patient, operating on scales that make all human concerns seem trivial. The stars will shine for billions or trillions of years, following the laws of physics, transforming matter and energy, creating light and heat, before finally fading. We are fortunate to exist now, in this era, when the cosmos is full of stars and galaxies, structure and light. We are living in the universe's prime, the era when star formation is still ongoing, when galaxies are still evolving, when the cosmos is rich and complex and beautiful. The future will be darker, quieter, emptier, but it's so far away that it has no relevance to anything happening now or in the imaginable future. The stars have been our companions throughout human history. We've navigated by them, told stories about them, used them to mark time and seasons, wondered about them, studied them, and gradually come to understand what they are and how they work. The stars are not eternal, but they're patient, shining for timescales that dwarf human history, that make our brief lives seem like quantum fluctuations, here and gone in an instant. And yet, we are part of the cosmic story, made of stardust, connected to the stars through the atoms in our bodies, through the light that enters our eyes, through the shared history of the universe. Every culture in human history has looked up at the stars and wondered, has created myths and legends, has used them to navigate and to mark the passage of time. The stars have been constant companions, unchanging on human timescales, reliable markers in a changing world. The concept of deep time, the vast timescales on which geological and cosmic processes operate, is difficult for human minds to grasp. 1,000,000 years is incomprehensible. 1,000,000,000 years almost meaningless. 1,000,000,000,000 years beyond imagination. Yet these are the timescales on which stars operate, the timescales that govern stellar evolution, galactic dynamics, cosmic structure. The universe is 13.8 billion years old, but it will continue for trillions upon trillions of years, gradually transforming, slowly fading, patiently following the laws of physics wherever they lead. We exist in a brief moment of cosmic time, witnesses to a universe in its prime, and that makes our existence all the more precious, all the more remarkable. And so tonight, as you finally surrender completely to sleep, imagine the stars shining in the darkness, billions of them, each one a sun, each one following its own evolutionary path, each one contributing its light to the cosmos. The stars are patient, eternal on human timescales, yet finite on cosmic timescales. They're born, they live, they die, and the cycle continues, generation after generation, enriching the universe with heavy elements, creating the conditions for planets and life, transforming the cosmos from simplicity to complexity. You are part of this story, a brief arrangement of atoms that can contemplate the stars, that can understand, however imperfectly, what they are and where they're going. Let that perspective carry you into the deepest sleep now. Let the knowledge that you're connected to the stars, that you're made of stardust, that you're part of the cosmic story, let all of that settle over you like a blanket of starlight. The stars will still be shining when you wake, still following their evolutionary paths, still transforming matter and energy, still lighting the darkness. Rest now in the eternal echo of starlight, in the immense silence of the cosmos, in the knowledge that you are part of something vast and ancient and beautiful. Sleep now. Dream of stars being born and stars dying, of red dwarfs that will shine for trillions of years, and massive stars that burn bright and die young, of white dwarfs cooling slowly and black holes evaporating over timescales that dwarf the current age of the universe. The stars are eternal in their transformation, and you are safe in their light. Sleep now. The cosmos will take care of the rest. The universe is patient, and so can you be. Let the ancient rhythms of stellar evolution carry you into the deep restorative sleep you need. The stars are still shining, even now, even as you close your eyes, and they will continue to shine for billions of years to come. Rest now. You are stardust, and stardust you shall return, and there is peace in that knowledge. Sleep now. Dream of the eternal stars.